So in this presentation, I'll talk about T2S-Tensor, which is a language and a compilation framework to map tensor computations onto spatial hardware. So this work was done as a collaboration between Cornell University, Intel Parallel Computing Labs, Georgia Tech, and Tsinghua University. So tensor computations are everywhere, from data analytics like graphs and social interactions to machine learning like CNN and recommender systems, and scientific computing like finite element methods. Due to this widespread use of tensor computations, there has been a lot of push to deploy these tensor applications onto different spatial architectures like FPGAs, CGRAs, and ASICs. Microsoft Brainwave and Google TPU are few examples of that. However, there still exists a gap on how to map these tensor computations on different spatial architectures. Now, using a simple driving example of matrix multiplication, which is also known as GEM, I will show why spatial programming for performance is hard. So here I'm showing a high-performance GEM systolic array for FPGA. So this particular design takes two matrices, A and B, multiplies them together to produce the output matrix C. The boxes shown in blue implement the actual compute piece which are computing the dot products. The boxes, initially the matrices A and B are stored in the device memory. The boxes shown in orange and green implement the set of P's which read these matrices A and B from the device memory and feed them to the core systolic array for the computation. The boxes shown in red collect the results from the core systolic array and then write them back to the device memory. Now, if we look closer into this design, we can find that it consists of compute customizations in the form of data vectorization, where the reads of matrices A and B are vectorized, and the writes to matrix C are also vectorized. We can also find that there is loop unrolling in the form of 2D array of compute P's. We can also find communication customization in the form of data gathering. For example, the CDrainer P's are implement a gather network to collect the data. We can also find data forwarding within a single row of the compute P's, which forward the data of A matrix in the horizontal direction. And we also have data scattering within the feeder P's in order to distribute the data among themselves. And finally, we have memory customizations in the form of rotating registers in the compute P's and double buffers in the feeder and in the feeder P's. So now if we look at the code, the HLS code for this high-performance GEM systolic array, it consists of around 750 lines of code. And if we zoom into a small portion of this code, we can find that it consists of compute customizations like loop unrolling, loop tiling, data vectorization, and memory customizations in the form of buffers. This also has communication customizations in the form of data forwarding. So from this, we can see that in a high-performance design from HLS, the hardware customizations and algorithm are kind of entangled with each other, which makes these designs less portable, less maintainable, and less productive. So as we already saw, in HLS-based high-performance designs, different bits and pieces of the algorithms are kind of entangled with the compute customizations, memory customizations, and the communication customizations. So in order to solve this problem, we implement T2S, which takes the approach where it decouples the algorithm from different types of hardware customizations. So the way T2S does this is T2S allows the programmers to specify the algorithm in the form of a temporal definition, which is typically a functional representation of the algorithm. And the different hardware customizations are represented or specified by the programmer as a set of spatial mapping directives. Thus, by taking a temporal definition and spatial mapping directives, T2S is able to convert a temporal program into a spatial hardware, and hence the name T2S. So now let's see how T2S can generate the high-performance GEM systolic array that we have showed before. So to start with, the user or the programmer has to specify the algorithm in the form of a temporal definition. So for example, here the user is specifying, is declaring an output function C, and they are specifying that each element of this output function C has to be initialized with the value of 0. And each element Cij of this output matrix has to be computed as a dot product of the ith row of A matrix and the jth column of B matrix. Now, since the application size could be bigger than the actual hardware available, the user is trying to tile the loops I, j, and k into I, j, j, and kk loops. So with this, we will get a very simple 6-dimensional loop nest iterating over I, j, k, I, j, j, and kk. And the innermost loop body is computing the dot products in order to perform the matrix multiplication. Note that in the innermost loop body, we are using the I prime, j prime variables, which are basically using the I and ii variables to compute the effective address. So once the temporal definition is specified, T2S will map the entire computation onto a single hardware P. Now the user can go ahead and optimize this temporal program for a spatial architecture. So for example, in this case, the user identifies that the innermost loop body consists of 4 major operations: loading of matrix A, loading of matrix B, performing a map operation, and storing the results back into the C matrix at the appropriate location. So the user isolates the loading of matrix A into a separate function called A feeder using our isolate producer directive. So this creates another function A feeder, which consists of exactly the same loop nest as we had in the C compute function. However, this A feeder just does nothing but just loads the values of the A matrix and send them using the channel CH1 to the main compute P C. The WCH primitive here stands for the right channel operation. So now, after the isolation of A feeder, the user can unroll the II and JJ loops in the C compute P, and this will create a 2D array of the compute Ps. Now, since previously A feeder was supplying the data to C compute P using a single channel CH1, and since we have unrolled the CPs, we also replicate the channel CH1 into a 2D array of channels, which is shown here as a 2D array. Now the user can go ahead and optimize the A feeder function further. For example, here the user further isolates the loading of the matrix A from A feeder into a separate function called A loader. And similarly, now A loader and A feeder are connected using the channel CH2, and A loader is actually loading the values of the matrix. Now the user identifies that the loading of matrix A in A loader does not really depend on the loop variable JJ, and hence they can remove the loop JJ from the A loader, and this will reduce the number of DRAM accesses from the main memory and should improve the performance. But now, because we have already removed a loop in the A loader, and A loader and A feeder had a producer-consumer relationship, removing a loop in the producer but not in the consumer actually breaks this data flow relationship. Hence, in order to recover this data flow relationship, the user inserts a buffer in A feeder at the appropriate loop location. In this particular case, this loop location is II. And now A loader and A feeder are connected using channel CH2, and A loader sends the data of matrix A using CH2 to A feeder. A feeder reads the channel and writes the values to the buffer, and further it uses the values from the buffer to feed the systolic array of the main compute Ps. Now the user can also specify the forwarding directive, which will create a forwarding network within the same row of the C compute Ps, which is also known as the systolic communication. User can unroll the A feeder piece and then create a scatter network using our scatter directive. And the user can further isolate C drainers and C collectors from the main compute piece C and use our gather directive to implement a 2D gather network. Now, with these optimizations performed on A matrices and A matrix and B matrix, and few other optimizations, we get this 20 lines of code as compared to 750 lines of HLS code that we had seen before. And as we can see, it consists of, first of all, temporal definition. Then it has compute customizations in the form of loop tiling, compute partitioning, data vectorization, and loop unrolling. And it also has memory customizations in the form of loop removals and buffer insertions. Finally, we have communication customizations in the form of data forwarding, data scattering, and data gathering. So with these 20 lines of code, we can generate the exactly same hardware that we had shown before. Now let's talk about the T2S compilation flow. So in T2S, the user or the programmer has to first provide a T2S specification. This T2S specification or T2S code is then compiled by the T2S compiler into extended halide IR. For the host part, T2S generates a LLVM code, which is then compiled into a binary and run on the host CPU. For the FPGA, currently T2S generates OpenCL HLS code, which is then compiled by Intel Altera AOC compiler and run on Intel FPGAs. And finally, for CGRA, T2S generates CGRA assembly, which is then processed by CGRA compiler and mapped and routed onto the CGRA, and further simulated by our CGRA simulator. Now let's talk about the evaluation results. So we compare our GEM implementation with the open source ND range style OpenCL code, which serves as the baseline. And we also compare our design with the handwritten and manually optimized design from industry, which is a Ninja implementation. And these are the results. So as we can see, baseline design uses 70 lines of code, while T2S uses only 20 lines of code, which are 3.5x less number of lines. And Ninja implementation uses 750 lines of code. In terms of DSP, the baseline implementation utilizes only 68% of the DSPs, while T2S and Ninja implementation both use 84% of the DSPs, which is a pretty high DSP usage. And finally, in terms of throughput, baseline implementation achieves a throughput of 311 gigaflops, while T2S achieves 549 gigaflops and Ninja implementation achieves 626 gigaflops. So thus, with T2S achieves 1.8x speed up over the baseline with just 3.5x lines of code, and it achieves 82% performance of the Ninja implementation with just 3% of lines of code. So using this language and compilation framework, we implement some other tensor decomposition kernels like MTTKRP, TTM, and TTMc on both CGRA and FPGA. So here are the results for the CGRA. As we can see, for all the 4 benchmarks, GEM, MTTKRP, TTM, and TTMc, the FMA usage of all the designs is very close to 100%. And all of these designs achieve a performance which is close to 100% of the Ninja GEM implementation. For the FPGA side, we can see that MTTKRP achieves a throughput of 700 gigaflops, TTM achieves a throughput of 562 gigaflops, and TTMc achieves a throughput of 738 gigaflops. And the DSP utilization of these benchmarks is also high. For example, in case of MTTKRP, it is around 80%. For TTM and TTMc, it is more than 90%. Thus, with almost close to 100% FMA usage, T2S is able to achieve close to 100% throughput of the Ninja GEM implementation for CGRAs. And with 80 to 90% DSP utilization, it achieves 560 to 740 gigaflops for FPGAs. And finally, to conclude, T2S provides a concise yet expressive programming abstraction that decouples spatial mapping from temporal definition. It identifies the set of key compiler optimizations, which are essential for creating high-performance spatial hardware for tensor kernels. And finally, we demonstrated high performance for 4 different tensor kernels on both FPGA and CGRAs. So thank you for listening, and I'll be happy to take any questions.
Do you have any questions? Any questions for the audience? Yes, one question. Microphone right back there.
Hi, I have a question about your baseline gem kernels. So that's the one that we can download from the OpenCL design example, right?
Yes, so this is the one that you can download from the Intel website. It's a yeah.
For that kernel, I'm just wondering what is. I remember it is a blocking implementation of gem, right? And do you remember the block size of that for that baseline?
It's I guess 64, but I'll have to
64 by
check.
64, right?
Yeah, and
Okay.
vector length was around 8, but I can recheck that.
Yeah, because I recall that actually Intel also provides a proprietary gem kernels.
Proprietary, is it open source?
It's not open source, but I think it can reach about one T flops. So I'm not sure if you are aware of that.
On which FPGA?
On
Bunty.
Arria-10. I think
Arria-10.
they had some slides previously, a few years ago. I forgot which conferences, but
Okay.
they mentioned about their proprietary gem kernels.
I think I can check that.
Yes.
Yeah.
Okay. Thank you.
Thank you.
Any other questions? No. Okay, thank you.